Hello everyone. The purpose of this video is to get us started in section 1.1, learning the first few things we need to know for that section. I'll let you know that most of these videos will start with a meme like this one. If we're meeting in class, I always like to start the class meeting with a meme and usually some announcements, and since we can't do that right now, this is going to be my way to do the meme thing. So you'll see one of these again pretty much at the beginning of most videos that I post for you. All right, so jumping right into it. Section 1.1, we talk about what are called functions. So a function, from the definition in our book, is a rule for a relationship between an input or independent quantity and an output or dependent quantity in which each input value uniquely determines one output value. We say the output is a function of the input. Now you see some recognizable vocabulary there with the terms inputs and outputs, or independent and dependent. And so what we're really talking about here are inputs and outputs. And just to be clear, this idea of a function, though, we'll look at it with numbers and formulas and tables and graphs. It really applies to anything where you put something in and get stuff out from it. Okay, although to be a function, there is a particular way that those inputs and outputs have to be related. So as a basic example of this, you create a couple of circles here. And the left circle, that's going to represent my world of inputs. And then the right circle there, that's going to represent my world of outputs. Okay, and generally the way a function will work is we'll have some numbers listed over here in the left. So let's say we have 2, 3, and 4. And then over here in the outputs, we have some other numbers, 5, 6, 7. And then a function is a rule, as it says, that tells us to do something with one of these inputs in order to get one of the outputs over there. So we don't know what the rule is or if there's a formula or what, but let's say it tells us to take 2 and map it to 6, 3, map that to 7, and then 4, map that to 5. Now this is an example of a function because notice that each input, each thing there on the left, goes to a single output. Okay? If we had something like where the 2 was going to 6, but it was also going to 5, well, that's no good. That is not a function. For a function, each input has to go to a single output. Now, one thing we can have in functions, though, is that multiple inputs can go to the same output. So, for example, if our function looked like this, so let's say that 2 went to 5, 3 went to 6, but then 4 also went to 5. Well, that's okay, because even though 2 and 4 are both going to the same output, what's important here is that each of them is only going to 1. 2 is only going to 5, and 4 is only going to 5. It's not 2 goes to 5 sometimes and 6 other times. Okay, that's what makes it a function. All right, one kind of real-world example I like to think of with functions is a soda machine or a pop machine. I know the debate rages on about which of those terms is appropriate. So let's say this is a pop machine or a soda machine, and they usually have buttons on them, right? Okay, so these are my buttons, and in this I'm going to use P to stand for Pepsi, C to stand for Coke. So let's say this button here, you press that, gives you a Pepsi. This button here gives you a Coke. Let's say this one also goes to Pepsi, and this one goes to water, which I still don't understand. Why do people get water from vending machines? Like, I mean, maybe in the era of COVID, you don't want to use a water fountain, but we have disposable water bottles. I don't know. That's neither here nor there. Okay, now generally a soda machine represents a function because if I press this button in the upper left here, okay, it's going to give me a Pepsi. And every time I press that button, it should give me a Pepsi, right? So for each input, input is pressing that button, it always gives me the same output. It always gives me Pepsi. Similarly, for clicking or pushing the button here on the right, upper right, push on that, it's always going to give me Coke. I'll never push it and get a Pepsi. And this lower one on the right here will always give me water, and that's what makes this a function. Now notice this one in the lower left here is also a Pepsi button. Okay, so it would give me the same thing as the one above it, but remember, it's okay for two inputs, and in this case our inputs are the buttons, to have the same output. So both of these here output Pepsi. What's important is that every time I press this button and every time I press the one above it, I get Pepsi. Okay, that's what makes it a function. Now, for those of you who have been on the Fort Steilacoom campus and in the Rainier building, you may know that there is a soda machine just outside of the hallway where math professors have their offices. That is not a good function, because sometimes when you press Coke on that, sometimes you get Coke, but sometimes you get Sprite. So that one's a bad example of a function. All right, so additional examples. So thinking about some inputs and outputs and whether or not they could represent functions. So we have two situations here. The first one says, could phone number be a function of student name? Now, first of all, we have to decipher the language here. So it says phone number is a function of student name. So first thing we need to do here is identify our inputs and our outputs. Now, because we're saying phone number is a function of student name, in that case, we're saying the student name, which I'm going to represent with SN, is the input, and phone number is the output. And the question is, would this represent a function? If I put a student's name here, let's say we have a student named Joe, and it gets mapped to a phone number over here. Okay, will that represent a function? Now we got to think about again what a function means. So each input can only go to a single output. Now let's say that Joe's name goes to his cell phone number. So far that seems like a function because his name is just going to his cell phone number. But could it ever go to something else? Well, if Joe has a landline for some reason, which are becoming more and more obsolete by the day, his name could also be mapped to that landline number. In this case, notice this is now not a function because Joe's name is going to two different outputs. So it's an example of something that is not a function. Okay, so turns out that one could not work. That could not be written as a function. So let's look at the second possibility here. So they say, could student name be a function of phone number? So now we're going to switch it. Okay, so now we want to think about if phone numbers were the inputs and student name was the output. So for example, we could have over here on the left that cell number and landline number for Joe. And we have Joe's name over here. And if we do that map backwards, we'll now notice the cell number is going to Joe and the landline number is also going to Joe. And so far, it looks like this is a function because each input, even though they're going to the same output, they each go to only a single output. However, at Pierce, we have a lot of families where multiple people from the same family attend classes at our college. So let's say that Joe's daughter is also a student at Pierce. Well, then potentially both the cell number, but definitely the landline number would also get mapped to Joe's daughter. And again, look, that now becomes not a function because we have an input here that's going to two different outputs, and that's not allowed. Again, for a function, each input can only go to a single output. So this one also does not work as a function. Okay. All right. Let's look at what is called a one-to-one function. So we've talked about how multiple inputs can go to the same output. Now, one-to-one function has some restrictions on that. So here it tells us that sometimes in a relationship, each input corresponds to exactly one output, and every output also corresponds to exactly one input. We call this kind of relationship a one-to-one function. So let's look at how that would play out. So again, I'll use these two circles here. Here on the left, we have our inputs. On the right, we have our outputs. Okay, I'm going to list my inputs here, 2, 3, 4, and say my outputs are 5, 6, 7. And let's say we have it where 2 goes to 5, 3 goes to 6, and 4 goes to 7. Well, this here is what we would call a one-to-one function. And just so you know, sometimes we'll use this notation here, 1-1 to mean one-to-one. And that's because, again, each input, not only does it go to only one output, each output is only related to one input, right? And so that output is unique to the input. So 2 goes to 5, 2 is the only thing that goes to 5. 3 goes to 6, 3 is the only thing that goes to 6. 4 goes to 7, and 4 is the only thing that goes to 7. Okay, so that's an example of a one-to-one function. Now, if we had an example where 2 went to 5, 3 went to 6, but then 4 also went to 5, well, now this is not one-to-one. Okay, and the reason for that, let's just say not one-to-one, is because 2 and 4 are both being mapped to the same output. So that's something that makes it not one-to-one. Okay, so for one-to-one, again, each input goes to a unique output. It doesn't share any outputs. All right, last thing for this video is function notation. So let's look at an example where student name is a function of student ID number. Now, this is an example of something that is a function because each student name is associated with a unique student ID number. Okay, and what I'm going to do here, first of all, is introduce some variables. So I'm going to introduce the variable n to represent student name. Student ID number, I'm going to use the variable I. And then when we do this, we also like to give our functions names. So I'm going to use f to represent that. Although it doesn't always have to be f, you can use g, h, k, n. You could even use I. Any of these things can be the name of a function. All right, and the way function notation works is we start by not drawing, but writing our function name, so f. Put some parentheses here. And then on the inside of the parentheses goes the input. So in this case, since student name is a function of student ID number, our input here would be I. So that's where the input goes. And then that equals the output. So in this case, the n. So that is our output. Okay, and this is read as f of I, not f times I. F of I equals n. And again, that's telling us that we input a student ID number here, and it outputs a name, right? So an example of what this might look like a little more concretely is if we did say f of 1, 2, 3, 4, which is not somebody's ID number, but as an example, f of 1, 2, 3, 4 equaled Cody as the name. Okay, so that's how this function works. Again, the input goes on the inside, the output is represented here. Now, some notation or some confusion that often arises with this is if you see something like f of 1, 2, 3, 4, okay? This is not the input. The input is just 1, 2, 3, 4. f of 1, 2, 3, 4 is representing what we get when we plug in or put in 1, 2, 3, 4 into that function. So f of 1, 2, 3, 4 is actually representing our output. That's a common misconception that I see with some students. Okay. So just to wrap this up, down here at the bottom, you'll see the definition from our book about this. So the notation output equals f of input defines a function named f. This is be read output is f of input, or more commonly we say f of input is the output. All right, that's all for now. Thank you for watching.